Hello, my name is Boulan Hamoud. I would like to describe a paper on nanostructure of STS micelles in water. This is a paper that just appeared 2013 last year, Journal of Research NIST. STS surfactants form micelles because they have a hydrocarbon core, hydrophobic, goes into the core, and then hydrophilic ionic surface. These micelles are not spherical, they're ellipsoid. And we found that their size shrinks with increasing temperature as well as with decreasing concentration. We use small angle neutron scattering along with mean spherical approximation model to obtain the calculated micelle volume fraction, which was lower than the STS surfactant volume fraction. What does it mean? This means that the part of the STS micelles do not participate in micelle formation and remain homogeneously mixed in the solvent. A set of material balance equations allowed us to obtain STS fraction or concentration in the micelle. The micelle aggregation number is also found to decrease with increasing temperature and decreasing STS fraction. This is a review of the literature. There's a lot of work on STS using sands. A number of samples have been prepared, 0.5% STS in deuterated water, 0.1, 0.5, and so on. A number of temperatures have been measured for all of these samples, from around 10% all the way to 87%. Trends observed in SANS data, like fixed concentration, varying temperature. When we heat up, the SANS intensity goes to higher Q. So you see the main peak, the structure factor peak. You see drop here, drop off 1/Q4, that's the foam factor, for the exponent of -4. There's a shoulder here, which tells us that these are not spherical, but there are two sides, it's ellipsoid. Here fixed temperature but varying volume fraction, STS volume fraction. So when we increase the volume fraction, of course the peak goes up like crazy because the STS are better formed, the micelles are better formed. It moves to higher Q, means the micelles are getting closer. Here, in the case of 21 degrees, we're showing also varying the STS volume fraction all the way up to 10%. We have the ellipsoidal micelles, and then higher fraction, we see a very strong low peak show up, as well as bragg peak show up here. This is almost like clustering. So this is at very high fraction. We'll find out why this low Q peak shows up. The bragg peak, this bragg peak defines interlamellar despacing between STS rich layers and the hydrated crystals. So this low Q peak is due to the formation of hydrated crystal separation by, in other words, STS crystallizes for these high fractions and this temperature. There it is again. So we see at low temperature, the peak is very well defined. These are definitely crystalline STS. There's a bragg peak, there's a low Q. Then when we heat up, we see that the micelles form, 21 degrees, and they remain at 30 degrees, but the low Q, the crystals melt. They melt at 21 degrees, basically at 30 degrees. There are crystals here, no crystals here. So in other words, crystallization amorphous here, crystalline. We'll not go over the model again. Anyway, you're welcome to read the paper and get all of the details and so on. So this is what we focused on, the 5%. We described it rather well here, before, and we see the ellipsoidal, oblate ellipsoid micelles here. We see the low Q power law, and it looks like the fit is pretty good. We can get the half axis of the ellipsoid, A and B, RA and RB, and they go down with temperature. So in other words, the volume goes down with temperature for the various fractions, but it goes up with volume fraction fixed temperature. So here we see the charge. The charge goes up with mass fraction, as it should, because there is more STS. Should mention that these are ionic micelles. In other words, there's a charge on the surface. STS is charged. Here we added some sodium chloride salt, and like 1, 2, 3, 4 concentrations of sodium chloride salt from 0 all the way to a half 0.5 molar. So when we increase salt concentration, we see that the minor axis becomes flat, saturation. The major axis increases tremendously. What does it mean? It means that these oblate ellipsoids, in other words, they're just like pancake. They'll grow laterally, but will not grow that much as far as their vertical dimension. So something interesting is the ellipsoidal volume fraction that we get from the fit, this phi fit, is systematically lower than the STS samples mixing fraction that we have from mixing the samples. What does it mean? This means that not all STS material takes part in micelle formation. Some of it remains homogeneously dissolved in the solvent. Like here, for example, when you look at the micelle volume fraction versus STS sample mixing volume fraction, we see the linear behavior here, but at the very low and very high fractions, it's not linear anymore because of saturation. So we cooked up a set of material balance equations where we defined the fraction of STS found inside the micelles, FSTS, the fraction of water included in the micelles, FD2O, total number of STS and D2O molecules in the sample, NSTS and S and D2O. The micelle number density, we called it N over V. Big V is the volume of the sample. Set of material balance equations, conservation of volume, definition, conservation of the volume fraction, the mixing volume fraction for STS, sample mixing volume fraction. So we have the fitted volume fraction and we have the mixing volume fraction, phi. The scattering line density difference. So we can combine equation 224 and get equation 1 here. So we have a relationship between volume fraction for mixing that we know and the volume fraction from the fit in terms of the relative fraction of STS inside the micelles. We still have equation 5, so combining these two, we get linear equation. So we can plot the STS fraction inside the micelle in terms of all of the other parameters. So solving this, we get the volume fraction of water, heavy water, and STS inside the micelles. So we need a lot of parameters in order to solve these material balance equations. But we got some good results. For example, the 1% STS volume fraction. We found that there's about 80% of the SDS is inside the micelles. 20% remains outside. Just a reminder about the definition of the CMC, critical micelle concentration. So micelles form when the SDS fraction reaches this CMC. Added surfactant goes to forming the micelles, while the surfactant remaining dissolved, doesn't participate in micelle formation, remains close to the CMC. In this case, for SDS in water, is around 0.2%. So, in other words, for the 1% STS fraction that remains dissolved corresponds to 20% of the content. So in other words, everything is fine. In other words, the results of these material balance equations agrees rather well with what we know about the CMC of this micellar system. So we see that 20% times 1% is 0.2. That's the CMC. Anyway, the SDS fraction and the D2O fraction inside the micelles. So we found that D2O is pretty close to 0, so there's no water inside the micelles. And the STS fraction remains pretty close to the CMC fraction. Okay. We also obtained the micelle aggregation number, which goes down with temperature. Looks like heating up softens these micelles. They get smaller. Since they get smaller, there's less material inside. So in other words, doing fitting to the model and then following through with a set of material balance equations, we get more information that way. Like for example, the 1% STS sample at 40 degrees C is characterized by a half-axis around 14 and 21 angstroms respectively. These sizes are comparable with the previously reported dimensions of 12 and 20 angstroms in the literature, the same system. The highest STS fraction of 20% and lowest measured temperature of 11. Another phase was observed. Two characteristics include RAG peak, high Q, strong low Q signal, point to hydrated STS crystals. So we're able to observe crystallization of STS, low temperature and high fractions. So another result, ellipsoid volume was found to decrease with increasing temperature and decreasing STS fraction. In the case of salt addition, sodium chloride, the ellipsoid micelles half-axis were found to increase with increasing salt addition. Salt addition seems to screen charges on the micelle surface, thereby allowing micelles to grow laterally while remaining of the thickness of one STS close to stressed molecule. Around 1% STS, it was concluded that not all STS molecules participate in micelle formation. Small fraction remains homogeneously dissolved. Material balance equations were derived, and for the 1%, for example, we were able to confirm the fact that the 20% remain dissolved in the water as participate in the micelles. Anyway, thank you very much. Check it out. Please read the paper.